Okay, so here's the Klein-Gordon equation. It was supposed to be the quantum equation of motion, the wave equation for a free particle, and it's relativistically invariant. The reason it's called the Klein-Gordon equation, or the Schrödinger equation, is that Schrödinger abandoned it. He did that because it kept predicting things that were wrong, like an access to infinite negative energy and things like probability going negative. Now Dirac wanted to fix this. He wanted to fix it by trying to get rid of these negative energies, or equivalently by getting rid of these second-order derivatives. So the eigenvalues of the Klein-Gordon equation obey the correct relationship, but this has positive and negative roots, and we can't just ignore all the negative roots because that corresponds to half of our basis set that we need. So Dirac's first idea was, well, why don't we try and make the wave equation have a square root in it, and then whatever its solutions are will form a complete basis. And so our wave equation would be based on this, and then we just convert that, and then we end up with a time derivative from our energy and a spatial derivative from our momenta. And of course, relativistically speaking, that's even worse than before, because instead of having second order in momentum and first order in time, what we have is first order in time and this crazy order. If we take a Taylor expansion of this, this is all orders in derivatives. So that's a crazy equation. So he was thinking, well, maybe that's not the way to go. What I really want to do is I want to get a first order equation that if I square it, I would get something like this, but it's correct in itself, and it will have, therefore, the right set of eigenstates and eigenvalues. So if we go back to first principles, we were trying to get derivatives of our field. Now, derivatives of our field, that's obviously a vector. So in order to make that a scalar, we're going to have to contract over something. And if we're not going to contract over more derivatives, we're going to have to contract over something else. So let's just invent something. So this is a set of prefactors. So that set of prefactors is going to have to contract down and give us, when we square it, the Klein-Gordon equation. In other words, what we've got here is just this expanded out. So A, B, C, and D are just the different components of this thing, gamma, whatever it may be. And what we want is for these two things to be equivalent. So if we square this, we will get the Klein-Gordon kind of term. We can almost exactly say what A, B, C, and D have to be. A squared has to be 1 on C squared. B squared has to be minus 1. C squared has to be minus 1, and D squared has to be minus 1. Are there things that when we square them we get minus 1? Sure, we've got imaginary numbers, done. But we also have to have all the cross terms go away. So in other words, we need AB, which is going to be the dt dx term, and BA, which is going to be the x dt term. They've got to cancel. So if this is 1 on C squared and this is I, this is not going to cancel. There aren't any numbers that do this. You can't have a complex number there and a complex number there and have this happen. So we're stumped. And Dirac was stumped too, until, as legend would have us believe, one night he was sitting in his room in St. John's College, staring into the fire, and he realized, if I need this kind of thing to be 0, all I need to do is to make these things matrices. In other words, he needed some kind of non-abelian algebra to do it, and the numbers, complex numbers, have an abelian algebra, and so he needed matrices, things that don't commute. Now, of course, if these gammas are matrices, then this thing, this phi, is going to have to be a vector, because these matrices are going to have to be acting on something of the same shape, or else we'll have illegal operations. So this will be a matrix acting on a vector. And so in fact, what he discovered was that there had to be more than one component to the wave function. Now this was an extremely exciting thought. It was an extremely exciting thought because it finally explained something that's been puzzling people for a long time. Remember when we went back into quantum mechanics and we discovered the existence of spin? For some reason, electrons didn't just have one component of the wave function, they had two components of the wave function. So when we put them through some magnets, we found that in fact they split into two components. And this was very surprising for a long time until people realized they could describe it by saying that the wave function had actually had two components. There were two kind of coupled wave functions for electrons. And indeed, this explains it. All we need here is 2 by 2 matrices, and these are 2. And we've explained from relativity why spin exists in the first place. So Dirac was deliriously happy. Then, a tiny glitch. It turns out that you can't get all of these things to be true. You can't get a squared, b squared, c squared, d squared, and these cross terms to be 0 with 2 by 2 matrices. What you actually need is 4 by 4 matrices. That's the smallest size matrix you can get all these properties from. And so he invented the Dirac matrices. So there's 4 Dirac matrices which have all the right properties to give us the Klein-Gordon equation back again when we square everything. And he discovered that we needed, in fact, 4 components to describe these particles. Now, if you've got a spin-half particle and it's supposed to have 2 components, then what you've kind of got is 2 too many. So to try to understand that, Dirac looked at the details of these matrices and their properties. And this is the anti-commutator. In other words, it's the AB plus BA kind of terms. And of course, we need these to be 0 when these indices are different, and we need them to be 1 or minus 1 when those indices are the same. So in fact, this is just the metric times the identity matrix. And these kind of properties allowed Dirac to figure out that in fact there were still the curse of negative energy states turning up here. So he had positive energies and he also had a big sea of negative energies, and he worked very hard to try and understand what's going on and rationalize it indeed. But after a lot of work, he eventually made a very bold prediction. He made the bold prediction that half of those energies were in fact going to be positive after all, because they belonged to a different kind of particle, an antiparticle for the electron, that actually had the opposite charge. And so the sign of the energy was flipped because the sign of the charge was flipped. In other words, he took his relativistic theory and made predictions explaining spin, and then made a prediction that it also predicted the existence of the antiparticle for the electron. The reason that was so amazing is that the antiparticle for the electron had not been seen at all. It had not even been suggested that it might exist. And then people went back to their cloud chambers, they went back to their particle physics experiments, and they indeed discovered the existence of the positron. And this was seen as an enormous breakthrough for theoretical physics, because for the first time we really saw a theoretical prediction of something that had not been seen at all turning out to be true. And it was based on putting together the principles of relativity and quantum mechanics. And so Dirac's equation for a spin-half particle and its antiparticle turned out to be, and we see that relativity is not just telling us exactly how the wave function should look, it's telling us about the kinds of structures that can exist in our universe. It's telling us about the kinds of mathematical structures that can describe matter and energy.